vending machine.
Spend all your money on this.
Huh?
Spend all your money on this.
Luckily, it's Costco. I like how this is funny to people about blue Skittles. There's something came up. Why the hell are there no blue Skittles? Yeah, the tropical ones are way better.
Real best Skittles are.
Yes.
And I would not take any questions. Sour Skittles.
Sour Skittles are also good.
They are the best.
I don't know about the best. You gotta be in like the right mood. Like mentally prepare yourself.
There is no wrong with Flora.
Ooh. Have you seen?
Water drink.
There's like these new watermelon ring candies with like tahini on them. Dude, they are so good.
I wouldn't say watermelon rings are exactly new.
There's lots of Rice Krispies and beverages. Also, apparently there's an American red, white, and blue Skittles mix.
Yeah. It can also be packaged to be an England mix.
There's a red, white, and blue Skittles mix apparently.
For America.
What? What flavor is the white?
Pina colada.
Yeah. Although I do like the white Airheads, even though I have no idea what flavor.
Well, there's different flavors each time. I'd buy
Oh
two.
my gosh. Yes.
Because the one got stuck. And I was so mad. And so I had to buy a second one.
Oh my gosh.
I wanted to get one. And then I was like, and it got stuck. And then it got stuck, and I was like, what do I do? What am I supposed to do? Just apparently. No. Yeah. But hey, now we both have skills.
Heck yeah. Anybody want Skittles? Oh, I've been wanting to go to Gold Rush, but they're only open two.
They're good. They don't always have it. It's like that one we discovered Father's Day.
Oh, nice.
And they were one of the vendors. I didn't even know about them.
Can I say I'm curious?
Also,
It used to be all the time before.
also, I'm slightly disappointed that the purple is not more vibrant.
I know. Neither is the pink. Like, I can't use the red.
The orange sure is though.
Well, is it the same?
There we go.
Do you know if the
You know,
Sugar.
wait. It's strawberry. No, I wanted cherry. My girlfriend absolutely hates cherry.
Mm.
So does her mother. It makes it really good because I got all the cherry ones.
Nice. Cherry Starburst, or?
Or just cherry in general. She hates cherry.
Yeah. Oh. What do you eat this cherry? What candies?
Oh. If I get, well, it also means if I ever get anything cherry, I don't have to share it.
Cherry Coke. Sorry.
She actually doesn't mind cherry Coke because
Ah.
it doesn't taste like it. Oh yeah,
Thank
I
you.
accidentally spilled a tiny bit of thing over there, so I swiped some paper towels from the lab. They're probably not gonna miss the paper towels.
No, they won't miss them.
I made sure the wet two soap and stay.
Do we come in next week?
Yeah, so next week, we're just gonna do review on Tuesday. I mean, it's streamed, so if you like can't come in, don't wanna come in, it'll be available online. And then Thursday, we'll do the final in person. If you absolutely can't make it, you can do it online.
I'll probably drop off the other two homework things Tuesday and just go.
Teacher, would you like a breast stick?
Oh my gosh, I would. I guess we're just eating the class today. I love bread.
You're welcome. Here you go. Sorry, I don't have any sauce to go with it.
Thank you.
Last night was, the high school graduation. So we went over to my brother's house, but it got out at the graduation only took like an hour and 15 minutes, which is like really good as far as graduations are concerned. They're really efficient because, there are like a ton of
This
kids.
is good.
So we went and got Pizza Hut, and then we went to Andre's house. My brother, he has like a little projector, and we were watching Free Guy, but we only got like 40 minutes into it because it was like 11:30 by the time,
Was it a good movie?
Oh, Free Guy is an amazing movie.
I haven't seen it at all, so.
I recommend you watch it. It is, if you know anything about video game design or like coding, it's like, this isn't really accurate. That's not really how AI works, but if you suspend your disbelief just a little bit, it's like,
Oh, you were so accurate about the Spider-Man. It's like, yep, just turn off. Yep, they could have sold it right there. Okay.
I know, right? Especially like at the beginning, like maybe just clarify what you want for the spell first.
Yeah, I know.
Like before you start it, you're starting a reality warping spell. Maybe just like, okay, so we want this, and this. Or
Yeah.
or Doctor Strange could have been like, sorry, nope, not happening.
Yeah, you were very accurate in your description.
And it's like, it's a good movie, but it's like you have to turn off your brain. It's like, you idiots, you could have stopped all of this so easily.
Yeah, I know.
Especially if you thought ahead and had just been like, hey, so, just in case, as a safety measure to make sure you don't try anything, I'm going to have a constant line with MJ. So if anything happens and like the phone call goes silent, she just presses the button. So don't try anything. She'll hear the commotion and you'll just disappear.
Yeah, they didn't do that.
Or even just like, all of them escaped. They kind of have my mother. MJ, please press the button.
Yeah. All right, let's get started with lecture. Sorry, we're having too much fun picking out apparently and eating Skittles. So I guess happy last lecture. So this will be our last official lecture. And then, so just a friendly reminder. So next week on Tuesday, we'll do review, just like we did before. So I'll have, the exam open. I'll make sure to hit all the topics that are going to be on the exam so you feel really comfortable. Thursday, the exam will be open for the online students. And then if you're in person and want to take it in person, then the exam will start 4 p.m. right here, same time, same place. And everyone will have the 2.5 hours, which again you shouldn't need, but I'm giving everyone plenty of time so that no one feels rushed or anything to do the exam. And then hopefully you saw my announcement. So the lab practicum, or the lab final, is live now. And so everyone's taking the same lab final online, so even if you're in person, online, all the same exams, so we're all in the same playing field. And so how that works is the lab is kind of based off of a few experiments that you've done. So I would, try to look over the pH one for sure. And the identifying the unknown compound lab. So look over your notes. So it's open note, open everything. Be expected to do other simple things that we've done, measurements. There could be density. Make sure you measure out correctly with a ruler, that sort of thing. So just kind of simple skills that you should have learned in lab. And so again, have all your lab reports ready. So if you're in person, I try to get everything back to everyone that's turned in stuff. So have old labs ready. Or even, just pull up all the PDFs again of the lab so you have all that reference information ready to go. And you have 2 hours for this lab. For the lab final, you should not need all that time. So there are 8 questions total. But 3 of those should be really quick. And the other 5 involve just a little bit more thinking and reading and slight analysis of what's going on in lab. And so you'll look at a picture or video that, again, it shows some experiment that you've done in lab before or very similar to something you've done in lab, and then you just analyze it. So any questions about the end here? I don't see questions in the chat. Hopefully the chat's alive and well. All right, so let's go ahead and finish up our last chapter then. So we kind of touched on this a little on Tuesday. But so water is really special in that it can undergo this auto-ionization. And so auto-ionization just means that it can kind of form ions. And so why this happens, and we were looking at this. So water is amphoteric. That means it can be an acid or a base. And so we kind of saw that on Tuesday, right? It depends what it's with, but either it's attacking with the oxygen to deprotonate or it's the proton source. But then this means, okay, so in just our random jar of water, that means that there has to be ions present then, if it has this ability to act as an acid or a base. And so it can act as an acid or base with itself. So about 2 out of every 1 billion water molecules forms ions through this process called auto-ionization. And just a quick recap of what this process would look like. So the first line, this is kind of why I would say this is an oversimplification of the process. You can think of it like that yes, it's splitting into a proton and hydroxide, but like we were discussing on Tuesday, you don't actually have just a lone proton in solution, so it's much more appropriate to think of it as 2 water molecules, like so, and then so one of these can just attack, electrons go back, and so that would give us our hydronium species and our hydroxide. And so again, every time you see this, that's just colloquially written as H+. And so what's kind of fascinating, and this now relates back to pH. So back when they're trying to figure out what pH is and try to understand it, what they realize is that, okay, in just a solution of water, they found that the concentration of H+ ions and hydroxide ions was both 1 × 10⁻⁷ molarity. And this is at your standard conditions, so just normal room temperature, 25 degrees Celsius. This is really important. And so let's look at why. So now we have this new relationship. And so this is the ion product of water. And so all this is saying is that if we take these concentrations, so 1 × 10⁻⁷ and 1 × 10⁻⁷ for both hydronium and hydroxide, then you can multiply them together and you get this Kw constant. So first they did it just normal plain water and came up with this relationship. And so now you're kind of seeing this is where the pH scale comes into play. And so if you multiply them together, you get this 1 times 10 to the negative 14th. And so now this is kind of telling you why, you know, your pH scale goes from 0 to 14 then. And so the other really key part of this is, again, it doesn't matter what your concentration is, so we'll look at different pHs, but the same relationship holds. So you multiply your concentration of hydronium times hydroxide, and it should always be equal to this 1 times 10 to the negative 14. And again, this is at 25 degrees Celsius, but for our purposes, we're always going to be at 25 degrees Celsius, so we'll always use this 1 times 10 to the negative 14 for your kW constant, but just know that this is temperature dependent. And so this means that these two concentrations are then inversely proportional, so as our hydronium or acid concentration, right, our proton concentration increases, then our hydroxide must decrease so that that product stays constant. And so now let's look at what this means in terms of pH. So all aqueous solutions contain both hydronium and hydroxide ions. And so we started off with our neutral solution, with our neutral water. And so they found, again, that neutral water has equal concentrations of hydronium and hydroxide. So again, both equal to this 1 times 10 to the negative 7. And so that means we can define an acidic solution as having more hydronium than hydroxide ions. And so that means our concentration of hydronium would be greater than 1 times 10 to the negative 7. And that our hydroxide would be less than 1 times 10 to the negative 7. And so conversely, this means basic solutions would have more hydroxide than hydronium. And so their hydronium concentration would be less than 1 times 10 to the negative 7. And the OH will be greater than 1 times 10 to the negative 7. So let's look at these examples. And so it says calculate the hydroxide concentration for each solution and then determine if the solution is acidic, basic, or neutral. So I'll give everyone a minute or two to kind of work that out, and then we'll go over the solution. And pull up my calculator. So did we get an answer for A yet? So either acidic, basic, or neutral, or we could calculate our hydroxide. So we just have our Kw is equal to hydronium times hydroxide concentration. And we said our Kw is 1 times 10 to the negative 14. I have to make some space here. So that means for A, what did you get for the hydroxide concentration then? Look in the chat too. So do we get this for our hydroxide?
Yeah, that sounds about right.
So all I did was take our 1 times 10 to the negative 14 divided by our hydronium. So now we have our hydroxide concentration. So 1.33 times 10 to the negative 10. And then, so does that mean this solution is acidic, basic, or neutral? Yeah, exactly. And so, right, it's acidic. We could either look at our hydronium here, so you can notice it's 10 to the negative 5th, so that's greater than 10 to the negative 7th, so that's a good clue. Or you could see that, that's pretty small. So yes, acidic. What do we get for B then? So either acidic, basic, or neutral, or did you calculate the hydroxide?
Wouldn't it be basic? I mean, sorry, yeah,
Nope, basic's right.
yeah, basic.
So basic,
Slightly basic.
slightly basic. And so we see our hydroxide concentration is 6.66 times 10 to the negative 6. And so that makes it just basic. I see it in the chat too, so 6.7 times 10 to the negative 6 for our hydroxide.
Wouldn't it be fairly close to pH neutral, or am I reading that wrong?
Let's plug it in. So we're about to get there.
Because pH neutral would be 1 times negative 10, sorry, 1 times 10 to the negative 7, right?
Yeah. And so you're like just ahead of where we are. So we're about to do the relationship between the concentration. So what we can do is let's plug it in and we'll see how close it is. And so the pH is equal to the negative log of our hydronium concentration. So I could plug that in. Let me not do that. So let's plug it in. So negative log of 1.5 times 10 to the negative 9th. And so that gives you a pH of 8.8. So I'm not sure like how close you were thinking, but
Yeah, that's fairly close.
and you can kind of see, you can kind of judge it by the power. That kind of gives you a rough idea. And then so last one, acidic, basic, or neutral here.
Probably fairly close to neutral.
So neutral, so yes, because we're at 1 times 10 to the negative 7. So we'll say it's neutral, and that means our hydroxide concentration then is 1 times 10 to the negative 7. And I see it in the chat too, neutral, so excellent. And so y'all did a pretty good job of identifying who is acidic, basic, or neutral, just based off these concentrations. But I like to compare things, and you probably will too, in terms of pH, just because that's a little nicer of numbers to deal with, and we're kind of familiar with this pH scale. And so let's look at what this means. So the acidity or basicity of a solution is often expressed as the pH. And so like I said earlier, our equation then is pH is equal to the negative log of our hydronium concentration. And so now we're really seeing where the pH scale came from. And so if we think back, okay, they found out that the H plus concentration in just regular neutral water was 10 to the negative 7. And of course, let's just do it so we can all see. So negative log of 1 times 10 to the negative 7 gives us back 7 there. So now we know this is why pH 7 is then considered neutral, since it's again based off of what they found for the concentration of water. We see why the scale goes from 1 to 14 from our Kw constant. And so this means anything with a pH less than 7 is acidic, and a pH greater than 7 is basic. And so we can also go back and forth. So let's say you were given the pH. You can determine the hydronium concentration by this relationship. So H plus concentration is equal to 10 to the power of negative pH. And that should look pretty similar to that pKa, Ka relationship as well. So everything's pretty related with the logs. So let's get a sense of the pH of some common substances. So we mentioned that stomach acid is basically HCl, and so you can see that in the pH of your stomach. It's about 1 to 3. That's also why, have you guys heard of like alkaline water? And I mean, some people swear by it.
Listen, I know this person who loves alkaline water with just a splash of lime in it. Just a splash of lemon in it.
Are you serious?
There was an actual post by this influencer who said they drink alkaline water in like just a little bit of lime or a little bit of lemon.
That's pretty funny.
It's hilarious.
But, so I'm not sure if alkaline water is a big scam, but some people think that it really doesn't make a difference because as soon as it hits your stomach, it's essentially getting neutralized, so.
But it's diluting your stomach acid a tiny bit. Ooh, so egg whites are actually a slightly alkaline food.
Yep, so egg whites.
I remember looking at a list of alkaline foods, and it had lemons and other citrons listed on
Oh,
it
that's
as
weird.
alkaline. And I was like, oh, so you mean alkaline. Like
Yeah.
they're alkaline in spirit.
That's why you can't always trust everything you read. And also those alkaline waters, I've pH tested them before and they came out pretty neutral, so I don't know if I trust them. But yeah, that's kind of an aside. But you can see, so lemons, limes, those are really low pH. That's also why, you don't want to kind of bathe your teeth in them, or I think I kind of mentioned it in before, that like magic goji berry that turns things, sour things sweet. You could kind of damage your enamel if you eat, obviously, too many sour things and go crazy.
Pro tip, after you drink soda, just eat a ton of baking soda. Or at least put a ton of baking soda in your mouth to counteract it.
That's an interesting thought. So soft drinks, pretty acidic, so I like the using baking soda idea. That's a good one. And then so plums, wines are also pretty acidic, so people also worry about the acidity of wines on your teeth.
And heartburn.
And heartburn, Good point. And so to counteract that heartburn, so if you
Drink some
notice,
milk of manganese.
of magnesia, yeah, so that has a pH of 10.5, so obviously basic, so that helps your upset stomach. Rainwater is a little bit acidic. And then human blood, notice that's a buffer, so it's kept at a pretty tight pH, so just a little above neutral. And then like household ammonia, a cleaning solution would be like 10 to 11. And then if you had even a weekly sodium hydroxide solution, that would still have a pH of 14. And so what do we get from this number? So of course we're seeing the lower the pH, the more acidic the solution. And so again, we're just looking at a scale from 0 to 14. In like research and other stuff, you can actually have like super acids that have negative pHs.
Super bases.
Not too familiar about super bases. Super acids are like a,
I think it's like just KOH, potassium hydroxide is one of them.
yeah, but I don't think that would be a super base. It's just like a regular base. And so if you notice with our log scale, so 1 pH unit corresponds to a factor of 10 in acidity. And so our normal pH range is just from 0 to 14. And so pH of 0 would be like a 1 molar solution of acid, so HCl, and a 1 molar hydroxide solution, like the potassium hydroxide, that would be 14.
But wasn't it since like a 4% was like a 14, wouldn't like a higher percent concentration be a lot higher?
Yeah, we could do the math on it. I'd have to like
I feel like you could
plug
reach,
it in.
considering it's by 10, I feel like you could probably reach a pH of 15.
Yeah, I mean, that's probably possible since, again, the pH could be negative if it's very acidic or larger than 14. So we could test that out. And so here's our pH scale, and you can see how it corresponds to our H plus concentration down below. So now try these two examples of A and B. So figure out, is the solution acidic or basic? And remember, you still have your KW relationship. Let's see if you can figure out the pH, and then acidic, basic, or neutral.
So for OH, would we start at 0 instead of 14?
So OH, what I would do for this one is use the KW relationship, but then we'll go over POH in a second, and then it'll probably make sense.
Got it.
So do we get a pH for this first one here, A? What do we get?
I got 3.7447.
So that sounds pretty good, just judging off of this -4. So
Shouldn't it be 1? No, never mind, that was something else.
and so yeah, 3.74 for our pH. Oops. And then is that acidic, basic, or neutral?
Fairly acidic.
So acidic. And then, so for this one, we'll discuss another way to do it in 5 seconds, basically. But for this one, I would use this relationship. And so we're given our Kw relationship, so we can find our hydronium concentration. So I'll first divide our Kw divided by our hydroxide concentration. So then that gives us our hydronium, so I'll write that down.
Is it a pH of 12.1139?
Let's see, so negative log. So 12.1139, yep. So hydronium, 7.69 times 10 to the -13. And so pH 12.11. And so let's look at another way to calculate pH, or find them all. And so now we could also express things in terms of pOH. So this is less commonly used, but still really helpful. And so we could also find the pOH. And so the pOH relationship looks fairly similar to the pH, except now it's dependent upon the negative log of the concentration of hydroxide. And we can also go the other way. So if we have the pOH, we can determine the hydroxide concentration. So same relationship, 10 to the power of negative pOH now gives us a hydroxide. And so now it's kind of the opposite effect. So if you notice for the pH scale, acidic was 0, basic is 14, and so the pOH is the exact opposite. So acidic is 14 and basic is 0. And so if you kind of look at this, you can already see kind of where this is going. So if you keep adding these two numbers together, they always give you 14. So again, going back to our Kw relationship. And then we also have this great relationship of pH plus pOH equals 14. So again, that's just directly related back to this Kw. So there's a short derivation here. So we have the two concentrations is equal to our Kw. Then if you take the log of both sides, so the log of this times this just equals your pH and pOH. And then, of course, the negative log of our Kw brings us back to 14. So we're full circle at pH plus pOH equals 14. So if we revisit this B question here, so we could have done a different way of solving it. So what we could have done is, so we have our hydroxide concentration, so we could go ahead and find the pOH instead for B. So let's plug that in. So negative log of 1.3 times 10 to the -2. And so that would have given us our pOH. So for B, POH is equal to 1.88. And so then we have our other relationship, pH plus POH equals 14. So then all we have to do to get our pH back out is subtract, so 14 minus 1.88. And so you would have the same answer. If I had rounded, I could have gotten 12.11. But you can see you get the same answer either method. So pH. So does that make sense? So hopefully this should feel really comfortable going forwards and backwards, so we can use this additive relationship and then either our POH and our pH relationships and go all around. So if you have the POH of something, you should be able to get the pH and then the hydronium, hydroxide concentration, so they're all related. So now let's look at what a buffer solution is. So a buffer is just defined as a solution that resists changes in pH when either an acid or a base is added to the solution. And that's due to because it has different components. So usually some sort of weak acid plus a salt, and that's going to be a conjugate base salt of that acid. So that's mixed together, and that's how you get a buffer. And so how a buffer works then is that you have components of the buffer that can either neutralize the acid or neutralize the base. Then we have this kind of equilibrium so that our pH remains relatively unchanged. And so that means buffer solutions have to contain either weak acids and its conjugate base or a weak base and its conjugate acid. And so we mentioned blood is kept at a tight pH, and so that is going to be a buffer system in nature. So it has carbonic acid and hydrogen carbonate as its conjugate base. And so you can tell, right, it's an acid-base pair, just the difference of a hydrogen. And so when selecting our kind of acid-base combination, we have to make sure we, again, pick the right conjugate base. So if we're making a buffer here, so we have acetic acid, and then, so you want to think about how it's going to behave in solution, so plus H2O. So this is going to get deprotonated to form our hydronium ion. And then that leaves us with acetate, so C2H3O2 minus. So this is our acid. This would be our conjugate base. And so then we can pick any salt then that has this as its anion. So they just pick sodium acetate, right? We could have picked potassium acetate, lithium acetate, so as long as it had that acetate component. And then again, it's important that you use a weak acid because you want to have this equilibrium behavior where it can go backwards and forwards, unlike, again, HCl. So I like bringing up HCl since it could not be a buffer, since chloride cannot act as a good conjugate base. So again, could not reform HCl. So this would not be a good buffer. And so what happens then when we add an acid? So we have, we have an acidic buffer. So what happens when we add a base? And so if we have a base with our acid, so of course they just react together in a neutralization reaction. So they'll form sodium acetate and then water. So those are our two products listed here. However, the pH of this buffer will only change a little bit, so it should just slightly increase. And so why that happens, so you have your neutralization, right? It forms your conjugate base here, your sodium acetate. But because it's all in equilibrium, after this reaction occurs, so you have your acetate in solution plus water, so it's going to go ahead and reform our acid there. So that kind of helps balance out that neutralization reaction. And so if the amount of sodium hydroxide that is added is less than the amount of acetic acid, then the pH change will be small. And then, of course, you could overwhelm it. So if you add, way more sodium hydroxide, then you have acid that'll just do a neutralization reaction and just be destroyed. So you can't overwhelm your buffer. And then with this buffer, if you add a small amount of acid then to our acidic buffer, so again we have acetic acid and our sodium acetate in there. So that means that our acid then is going to react with our conjugate base component, so it's going to react with our sodium acetate. So it'll be again neutralization reaction, so form sodium chloride. But then notice what the other product is. So that's reforming our acid, so getting back acetic acid, which again is in equilibrium with its base, so that helps mitigate the change of the pH. So that means that the pH of your buffer then will only decrease slightly or not at all. And so again, if the amount of HCl is less than the amount of sodium acetate, then you should have a small pH change. And of course, again, you can always overwhelm your buffer with too much. And so again, this is going over how they work. So for an acidic buffer solution, we're adding base to it. So again, we're forming our conjugate base of our acid, so forming acetate and water. And then we can have an equilibrium shift, so it'll shift back to reform that acid. So same thing with adding acid now. So the acid, again, reacts with that conjugate base. We make more of our original acid, and then equilibrium can be re-established. And so for our purposes of this class, we'll keep things simple. And so the easiest way to kind of calculate your pH then from this buffer is this equation. And so this works as long as the x is small, and what we mean by that is you want a factor of about 1 times 10 to the 4th difference or so with your pH. So if we look, so for all these, they'd be pretty appropriate. Chlorus is a little on the edge there with its Ka, since it's a little bit larger, of 10 to the -2. But for the most part, they're pretty small, and so we could just use this formula. And again, that's perfectly appropriate for the scope of this class. I don't want to get into too much of the weeds, but this again does fall apart if there's not a small, if there's not a large difference in this x is small approximation. And so all we have to do then is plug it in to this formula. And so you have pH is equal to the pKa plus log of your base over your acid. And so, right, this pKa is going to be from our weak acid. So we can, again, go back to our chart. There's our Ka, or pKa, I mean, for different substances. So if you were doing, you know, let's just look at acetic acid because that's what we're focusing on. So we're trying to make our acetic acid buffer, trying to determine the pH. So we have our pKa 4.74. And then we'd plug in, so plus a log of base over acid. So this is just base concentration over acid. So in the case of our acetic acid buffer, C2H3O2, so acetate would be considered the base. So you would take your concentration of sodium acetate, for example. You would plug that into your base over your acid, and then of course your acid in this case would be acetic acid. I don't remember if this chart is in the book. No, I stole it from another book, so I don't think this specific chart is in your book. I would have to look at your book to see if there's a similar one. But I'll post the notes after this so you can have this chart. And so the other thing that you should be aware of is you might see an alternate but really similar looking form of this equation. And so you may see it on your homework or different notes, but you may see an alternate equation. So pH is equal to pKa minus the log of acid over base. And so notice, right, acid's on top in this one, and now we have a minus sign. So personally, I don't like this formula just because I want to be consistent in my head. So usually I always use this one, but again, I don't want you to be alarmed if you see it, same exact formula, they would give you the same results. All right, so let's look at this next one. And so if you understand buffers, hopefully this should be relatively straightforward. And so let's look at how to classify salts, because this is important. We got to read through a lot of this together, so let's do this. So let's just read it, and then we'll kind of analyze it. So it says, if the salt cation is the counter ion of a strong base, and the anion is the conjugate base of a strong acid, neither ion reacts with water to affect its pH. Therefore, a neutral solution will be formed. All right, so let's break that down. So it says the cation is the counter ion of a strong base. So all that means is if your cation came from a strong base, then it's neutral. And so what does this mean? So an example of this is sodium hydroxide. So if we're looking at sodium, so we're analyzing sodium chloride here. And okay, well, sodium is from sodium hydroxide. That's a strong base. So that disassociates completely. And so that's not going to do anything in solution, right? This sodium is not going to reform with this hydroxide or anything. They're completely disassociated. So that's that first part. And then the second part is, okay, the anion is the conjugate base of a strong acid. And so let's check that out. So I like to break this down into an analysis. So we do our sodium. So again, it's from sodium hydroxide, so that's neutral. And so chlorine comes from HCl. And so remember, I keep emphasizing that this chlorine, right, can't reform. And so this would also be neutral. Because all this is saying is that if we have chlorine ions in solution, we're basically asking, can it reform and make HCl? The answer is absolutely not. The equilibrium lies all the way to the right. So it would just be hanging out as chloride ions. So in this case, sodium chloride is neutral. So does that make sense so far? So let's look at this next example. So calcium nitrate. So we'll do our same kind of analysis. So we'll start with our cation. So where does calcium come from? What base is it associated with? So what's just the simplest compound that it can form a base with? So you have your cation, so then you want to pair it with hydroxide, basically. So our calcium is from calcium hydroxide, right? So it's the cation from calcium hydroxide. This is a strong base. And so if this is a strong base, this means our cation is neutral. And then, so looking at nitrate then, so what acid is nitrate from? So what's the simplest acid you can make that has nitrate in it? Just try to stick an H on there in some fashion. And if you're struggling with this, I would reference, where's that other chart? So we had this chart here, right? And so this is really useful for this portion. So we can go back. Here we go. So nitric acid, right? So there's our NO3. So we see that the acid that it comes from is nitric acid. And then this is why I like this chart, because it gives us a helpful hint. And so it reminds us that these undergo complete acid ionization in water. So that means, right, they're not going to reform or anything. So if we go back to our acid analysis, so it's from nitric acid. So again, this means that in solution, the equilibrium lies all the way to the right. And that's telling us that nitrate will not reform nitric acid. So it's not going to try to pick up this proton or anything. So that would not work. And so that would make nitrate neutral. So any of these nitrate salts would be neutral. So like potassium nitrate, sodium nitrate, right? All those would be neutral salts. And then so now looking at KBr, let's do that same analysis. So potassium bromide. So we start with our cation. So what base does our potassium come from? So what's our base that we use all the time that has potassium? Yeah, potassium hydroxide, exactly. So if it comes from potassium hydroxide, so this is a strong base. So again, it's going to be fully disassociated. So that means that our potassium is neutral. And then, so what about bromine? What acid does bromine come from? always look back at our chart too. So which acid is it from? So I see HBr in the chat, so hydrogen bromide or hydrobromic acid. And so it's, again, I like this chart. It's reminding us, oh yeah, HBr is one of our strong acids. So again, it's going to be completely disassociated. So HBr, completely disassociated. Equilibrium lies all the way to the right. So this means that this bromine is not going to reform HBr. That would not happen. And so that makes bromine neutral. So do we feel good so far? Ask questions. This is always like the trickiest part for people. So let's try kind of the next scenario and see how we feel. So let's read through the jargon and then we'll break it down. So now it says if the salt cation is the counter ion of a strong base, okay, so we know this part already. So we know if the salt cation is the counter ion of a strong base, right, that makes that cation neutral, and it says it here. So the cation is pH neutral, okay, and we know that from our previous step. But now let's look at the conditions about the anion. So it says the anion is the conjugate base of a weak acid. So then that means that the anion is basic. And so that means a basic solution will be formed. So let's go through this analysis. So let's start with sodium fluoride here. So sodium fluoride. So we'll start with sodium. So sodium, again, comes from sodium hydroxide. So that's a strong base. So that means sodium is neutral. And so we know sodium is neutral. But what about fluoride? So is this acidic, basic, or neutral? So what acid would fluoride come from? Yeah, hydrofluoric. And then, so what do you remember about hydrofluoric? Is that a strong acid or a weak acid? We can always go back. Exactly, and I see it in the chat too as well. And there's our chart too to remind us, okay, it's a weak acid. And then it's not part of this. So this means, okay, we do have some sort of equilibrium. We could also look at that other chart. Okay, HF, I know there's some equilibrium. And you could also use this to kind of help you and remind you. So now let's see what's going to happen in solution. So let's just write out HF normally. And just showing, again, I'm using now our equilibrium arrows since it's a weak acid, so it can go forward and backwards. And so because it has this equilibrium, that means that if we have fluoride, so we have fluoride ions in solution, and we add water to that. So we already said that this fluoride then can go ahead and deprotonate this water. And so it'll reform HF, but then also produce hydroxide ions. And so because of this behavior right here, so it's our conjugate base, and I'll add this to, right, it's our conjugate base of our HF. And so this means that fluorine is basic. And it's basic, again, since it's producing hydroxide ions in solution. So back to our definition, anything that is basic will produce hydroxide ions. So feeling okay so far? So let's do the next analysis for this calcium acetate and confirm acidic, basic, or neutral. So calcium acetate. And so as you go through these, you can kind of do them faster and faster too, because once you establish whether a cation or anion is acidic, basic, or neutral, like it's always going to be acidic, basic, or neutral. So we've done calcium before, so we already know that calcium is from calcium hydroxide, so strong base, so that means calcium is neutral. So now we just have to worry about the acetate. And so what acid is acetate from? Let's look at our chart. So which acid matches? Yeah, acetic acid. And so we're looking at here, okay, acetic acid, weak acid. So we know it has equilibrium behavior. So let's write out kind of both scenarios. So we know that it's going to dissociate in solution. And so that means if we just have acetate floating around, so it's going to react with water then to reform our acetic acid. And so once again, right, that's going to produce hydroxide ions. So this means acetate itself is basic. And so that makes sense going back to our buffer, why we had our acetic acid and our sodium acetate. So again, we have our acid component and then our base component there. So then last analysis on this one. So let's look at this potassium nitrite. So K, let's switch colors. Oh man, I was hoping for more options. I'll do orange. Oops. So we've already established that potassium is neutral. So potassium, again, comes from potassium hydroxide. So potassium is neutral. But then our nitrite, so let's look at our chart here. And so there's nitrous acid, so HNO2. So we know it's a weak acid, we know it's in equilibrium. So we can write out our equilibrium expression. So we have, of course, our acid will dissociate to form nitrite plus our hydronium. And so since, again, it can go forwards and backwards, if we just have nitrite by itself plus water, it's going to go ahead and reform our nitrous acid, and then, of course, once again, make hydroxide from this water, and so that gives us a basic solution. And so something else, just kind of to note as we do this, so what you should start noticing is that your cations, they're either going to be neutral or acidic, and then your anion is either going to be neutral or basic. And that, again, kind of relates back to these basic properties, right? So we said that acids are substances that accept or need an electron pair. So it has to be something that's a cation, so that makes sense. why you're never going to have an anion that's an acid. And same thing, right, with the bases. So it has to have something that's donating, so it's not going to be your cation. It has to be either your anion or it's not. So hopefully that will help you. Maybe we should add that. So cation, it's either going to be neutral or acidic. And your anion, either neutral or basic. And so with that in mind, let's look at our last scenario here. Maybe not last, but. So we have, let's read through the jargon. So if the salt cation is the conjugate acid of a weak base, okay, and the anion is the conjugate base of a strong acid. So let's just look at this last part. So the anion is a conjugate base of a strong acid, so we know that that anion is neutral, and it goes on to say that, so we already have established that. But then looking back at this first statement, so the salt cation is the conjugate acid of a weak base, then that means that cation is acidic. However, what you'll kind of note is we really only have one option here, so this is one of our few cations that fits into this category. So we have very few cations to begin with in terms of these salts. And so ammonium is the only one that kind of matches here. So that kind of helps you. And so let's just go through the analysis so we can tell. So NH4Cl. So for ammonium, and so now we have to think back of where it comes from. So writing out a reaction, so ammonia plus water gives us ammonium plus hydroxide. So then that means if we have ammonium in solution plus our water, so now this means that water is going to act as a base to deprotonate our ammonium, and so this gives us back ammonia and then makes hydronium. So now we can see, okay, this is why ammonium is called acidic, and so now we can say that it's acidic. And then meanwhile chlorine, so we've already established that it came from HCl. Chlorine can't reform to make HCl, so that means chlorine is neutral, and the overall salt would be acidic. And then, so just a special scenario. So this is if the salt cation is a highly charged metal ion, and the anion is the conjugate base of a strong acid. So we don't really care about the last part. So anion, conjugate base of a strong acid, we already know that's going to be neutral. But this is really a special case with aluminum. And so sometimes aluminum reacts with water, and so it forms a bunch of aluminum hydroxide, but then that leaves H+ ions in solution. So then you would have an acidic solution. What is going on here?
Did you tap the middle mouse button on accident?
I don't believe so.
Yeah, 'cause it's not like the cursor thing.
That was really weird. So now I clicked it, so oh my gosh, now I can't unclick it.
Okay, click off the page. Like move to a new tab.
Okay, I think it stopped itself.
Okay. My computer loves to do that, and I'm not sure if it's just because of Chrome hating me or because my PC is old.
Ah. Yeah, I never know with computers. And then, so kind of the last little scenario is, well, what happens if we have this scenario like ammonium fluoride? So ammonium fluoride is a little awkward, right? So ammonium, well, we know that that's acidic, right? And then this fluoride, well, that's basic, but then, well, how do we know which is which? And so for this one, so HF is a stronger acid than ammonium. And so the Ka of ammonium is larger than the Kb of fluoride, so the solution would be acidic.
They cancel each other out, or if it was similar, it would just be neutral, right?
Yeah, if they happen to be exactly where the Ka is equal to the Kb, then yeah, it would be neutral. So that would be like a rare scenario, but
Could happen.
yeah, so we'll add that. So if Ka is equal to Kb, then it'd be neutral.
Aren't most salts neutral?
Yeah, yeah, most salts are neutral. So let's see if we can try this out. So determine if the solution formed by the following is acidic, basic, or neutral. So I'll give everyone a few minutes to look at that. I think we're kind of running out of time, so let's try to go over them. So what do we think about strontium chloride? Acidic, basic, neutral? So where does strontium come from? What base? So strontium's just from strontium hydroxide.
Okay.
So that would make strontium neutral. And then what about chloride? Do we remember acidic, basic, neutral?
Isn't chloride acidic? Oh, it's neutral.
Yeah, remember it comes from HCl.
Oh, right, where the H is specifically the acidic part, not the chlorine.
So A should be neutral. So what about B? So remember that was one of those special ones. So acidic, basic, neutral. Remember what we said about aluminum?
Wouldn't it be acidic?
Yep. So aluminum was one of those special ones that you kind of have to just know and remember. So it's our highly charged metal ion. And so yes, it would be acidic. And so bromine, of course, is from HBr. So bromine itself is neutral. And so that leaves aluminum as acidic. So overall acidic solution. What about C? So this was kind of a tricky one just because it might have been hard to identify what the, where it's coming from. So in the interest of time, so what you kind of had to recognize, so we have CH3, NH3, NO3. And so you could kind of see, okay, this is nitrate. So we can pick that part out. And so let's start. So we know nitrate, that's from nitric acid. And so that's neutral. But this one, does this kind of remind you of something? It might help if I draw it like this. What does that remind you of?
So it would be basic because it would attach to an OH negative. Would it be NH3OH?
Yeah, so it would be basic. Or, no, not basic.
Isn't OH basic, or did I just flip it on accident?
I think you flipped it. So remember, it's a cation, so it has to be either acidic or neutral. But then, does this remind you of something? What was our only, I said it was like our only cation. Right? It kind of looks like ammonium. So this is methylammonium, not to be confused with methylamine. So this would be the conjugate acid of methylamine. So methylamine would be this substance. Highly regulated, all thanks to Breaking Bad. So that's how you make meth. But so now, going back to this form, so we have, again, very similar, so methylammonium, so plus water, so we have a plus charge here, so that's going to want to form hydronium, just like it does in the case of ammonium, and we get back out now our methylamine, again, highly regulated substance, you would not be able to buy that without getting the feds all over you. And I see it in the chat too, so that means that C is overall acidic. And I know we're over time.
I thought the class got out at 6:30, not 6:20.
6:20. So we'll do the last one. So we already saw sodium fluoride. So the last one, so this one, sodium.
Nacho.
So sodium nacho over here.
Yay.
And so we see that sodium nacho really corresponds to this formic acid. So CHO2. And that's why I like this chart, so it kind of helps you relate them back.
Where can I find the chart?
I think I'll have to post the notes, because these are just from my personal things that I've acquired over.
Legally, right?
It depends who
No,
you ask.
pirated.
Technically pirated, because I no longer use this textbook, but meh.
I have nothing wrong, or I have no qualms without piracy.
So
Especially
this,
when it comes to textbooks.
so sodium we know is neutral. This is from formic acid. And so what does that mean if it's from formic acid? About this?
Neutral.
Try again.
Sorry, acidic.
Try again.
I thought you said it can't be basic.
The anion has to be basic. The cation can't be basic. So this would be basic, right? Because it reacts with water, reforms our formic acid, leaves us with hydroxide. So basic and overall basic solution. All right, I apologize for going over time. We'll end there for today, but I'll hang around in case there are questions. I know I kind of rushed the ending there. And so like I said, Tuesday, we'll go over everything. I'll have the exam, so you hopefully will go over exactly what you need to know. You'll feel really good and be ready for the final. And then don't forget, lab practicum is live and open.
What was the formula for POH?
So POH is equal to the negative log of the OH. All right, so thanks again. Y'all have been wonderful, both online and in person. I've actually really enjoyed this hybrid class. I think it worked out pretty well, especially with the YouTube experiment, and I appreciate the online people kind of being my guinea pigs for that. That's the first time I've done this as a class, streaming to YouTube, and so hopefully you like that. Look forward to feedback, and so thank you again. And I'll take papers, eat more Skittles.
Okay. So I was getting confused on number 8 for this homework.
Oh. So that one was like the Van Hoff factor.
I was trying to do that, but I didn't have temperature.
You don't need temperature. You just have to compare the ions. Damn it. It's annoying that there's never a marker. I'll just do it on here.
And then I was looking for osmotic pressure online, but was having a bit of trouble with it because magnesium chloride kept only showing it in like 0.1 or something, or like only had it in like 0.1, and I couldn't find the others correctly.
So osmotic pressure, remember that's just like related to the Van Hoff factor. So we go back to these notes. So do you remember this stuff where we were looking at like you have a 1 molar solution of sodium chloride, but then it's really like 2 molars effectively? So that's what you want to use for that part. So for that one, you're comparing a 0.1 molar sucrose, right? And so in solution though, it doesn't disassociate, so it's still 0.1 molar solution of sucrose. But then you want to compare it to, so you have a 0.08 molar solution of sodium chloride.
I remember sodium chloride having twice the vapor pressure of, or osmotic pressure as salt sucrose.
Right, so then, but
So
in
you
this
have
case,
more.
so it's, you would just multiply it by a factor of 2, right? So it splits into 2, so that means its effective molarity is 0.16 molar.
Yeah.
So does that make sense?
Yeah.